Good afternoon. We would like to welcome everyone online and in person to today's talk. Before we get started, I have a few announcements, actually two announcements, and then I want to explain to you the purpose of the series. So on this evening at 7:30 p.m. in the Whitaker 100 Auditorium, Richard Sandor will present a talk titled Good Derivatives, a Story of Financial and Environmental Innovations. And then on the 22nd of March at 4 o'clock p.m. in Siegel Hall, there will be a panel discussion and the topic will be Achieving a Fossil-Free Tomorrow. Washington University's Photosynthetic Antenna Research Center, PARC, and the International Center for Advanced Renewable Energy and Sustainability, ICARES, partnered in 2011 to launch the Events and Topics in Bioenergy series. The purpose of the Events and Topics in Bioenergy series is to provide an interdisciplinary perspective in bioenergy and the environment. Comprised of seminars and site visits, the series provides a unique opportunity to gain fresh perspectives on energy and the environment from renowned faculty and influential business colleagues. Through talks, field trips, and laboratory visits, participants will explore the range of current and future energy resources and sustainable solutions. While the series is targeted to undergraduate students participating and or interested in the Certificate of Accomplishment in Energy and the Environment, it is open to all members of the Washington University community and the general public. The 2013 series includes perspectives on solar energy and wind energy. The 2013 series also includes a visit to the Maryland Heights Renewable Energy Center. The Maryland Heights Renewable Energy Center tour is on the 9th of April from 3 to 5 p.m. Transportation will be provided. To RSV, please visit park.worcester.edu. Together, these seminars and site visits provide an introductory but comprehensive overview of major efforts in the region in energy research and sustainable solutions. Again, we would like to thank and welcome everyone online and in person for today's talk. We're pleased to have Dr. Joseph Cullen as our speaker for the hour. Dr. Cullen is an assistant professor at Washington University in the Olin School of Business. He studies the interaction between government regulations, business decisions, and the environment. Previously, Dr. Cullen was the Morgan Blake Environmental Fellow at the Harvard University Center for the Environment. He received his PhD in economics from the University of Arizona in 2009. Dr. Cullen is an economist who investigates the economics of energy and its implements for our environment. In particular, he studies electricity markets and environmental benefits of alternative energy sources. Please join me in welcoming Dr. Joseph Cullen.
So let me just get an idea of who I'm talking to. So how many here are engineers by training or in school? Engineers? Other sort of hard sciences? Okay, anyone else in sort of the law, economics, anthropology? Okay. Sort of, a little bit? Oh, you're a friend. So you can be anything you want to be. Great. So that gives me an idea of who I'm talking to. So today, I'm going to be talking on measuring the environmental benefits of wind power. And just to be clear from the outset, this is not as you'll see, is not a cost-benefit analysis of wind power, but rather just trying to measure what it is we're getting from wind power in terms of pollution reduction. This is a pretty important topic right now, given the growth of wind power in the US. So on this graph, we have total wind power installations in the US from the early 1980s up through 2007. And you'll see right around the year 2000, maybe 1999, we start almost this exponential growth curve. Right? And this growth has continued actually at a similar pace through the present time. So the growth in wind power has really been extraordinary. Right? We can break this out by where this, this power is being installed. The biggest portion of it up through 2007 actually came in Texas. So this part before actually was mostly in California due to some subsidies in the 80s. There was a large installed base there. But a lot of the growth has come from Texas and then from various other places, mainly in the Midwest. Okay, so why have we had this growth? This is the question I first asked myself when I was a graduate student. I'm like, what's going on here? Why are we having this tremendous growth? It turns out that the answer is fairly simple. It's because we're paying people to put wind power in. Right? We give them subsidies. In 2007, there was over $1 billion spent in renewable energy subsidies alone. Right? Why do we subsidize it? Because it's clean, green, and renewable. We like all of those things. To be more specific, it emits none of the traditional pollutants that we see from gas and coal-fired power plants like NOx, SO2, and carbon dioxide. And the idea is if we subsidize wind power, then other generators will have to produce less electricity. Right? In some sense, wind power is going to crowd out production from other energy sources. Right? So suppose that we have a grid with different power producers on the grid. We have coal plants, we have gas turbines, we have gas combined cycle, we have nuclear. Right? The idea is that wind is going to be built. It's going to produce electricity at certain times of the day that will flow over the electricity grid. Other types of generators will reduce their production. Now, it turns out that these different types of generators have very different emissions profiles. For example, you take a coal plant, it emits over a ton of carbon dioxide for every megawatt hour of electricity it produces. It also emits significant amounts of sulfur dioxide and NOx. You compare that to a gas combined cycle generator where you have less than a ton of carbon dioxide per megawatt hour, very little amount of sulfur dioxide, and also much less NOx being emitted. Then you have other types of gas turbines, which are somewhere in the middle. Here, this one is about 1,500 pounds per megawatt hour. Then, of course, you also have nuclear, which has its own set of environmental issues. But for the most part, and I'll explain a little bit later why, we're not going to be focusing on nuclear, primarily because it just doesn't respond to wind when wind produces electricity. It's not crowded out. Okay? Because the idea is we want to tell which of these generators are being crowded out. And like I said, nuclear is basically we're not going to worry about it because it turns out it's not going to be crowded out. But we want to know what is the distribution of offsets in terms of electricity across these types of generators. Because this is what will determine the environmental benefits of wind power. This is the objective, to answer this question. What do subsidies bias environmentally? If we're spent... Yes. And if I don't, come back to me in a minute, okay? So the question is, what do subsidies bias environmentally? If we're spending $1 billion a year on subsidies, I hope that we're getting something for it. Right? So in particular, I want to look at the quantity of emissions offset by wind power. And also, I want to look at the value of those emissions. How valuable are those emissions that are offset? And this is going to depend on these generator-specific substitution parameters, or which generators ramp down their production when wind power comes online. That's a very short-run effect. So if it's a windy day, there's lots of wind coming into the electricity grid, some generators are going to produce less electricity than they would have absent any wind power. Right? So that's a short-run effect. There's also a long-run effect. So if I have a gigawatt of installed wind power, people may install different types of generators on the grid, or certain generators may enter or exit. In this presentation today, I'm going to be focusing on the short-run effects. So given the landscape of the generators as they are, you introduce wind power, how are they going to change their production patterns? Right. So the long-run question is very interesting, and perhaps more important for policy considerations in the short-run effect. But it's not going to be the focus of today's work. That's something I'm working on in the future. Okay. So we're going to make an assumption here throughout the talk, and that is, without that we would have no wind farms without a subsidy. So if you were to take the subsidy to zero, or if we had never had a subsidy, you would see no new installed wind power aside from the wind power that was installed in the 1980s. Okay, so let's. Right, so the subsidy that I'm looking at is the production tax credit, the federal production tax credit, and that kicked in 1999. So that's the subsidy. That's the particular policy I'm looking at. So the subsidies for California, those are already, the ones that induce those investments are already gone. So I'm not looking at that particular question. Okay? So wind power is very capital intensive. You spend all your money up front. You spend $1 million for a megawatt turbine. And after that, it's very low marginal cost. You have to pay maybe some leasing fees on land. You have to pay for maintenance. But as far as generators go, very, very low marginal cost because your fuel is free once you install it. Subsidies come in both federal and state flavors. So the federal flavor is the PTC, or production tax credit. And there's, depending on the state, there may also be an RPS, a renewable portfolio standard. Those usually are paid out in something like some kind of environmental credit or renewable energy certificate. And between those two, for example, in the market that I'm looking at, I'm going to be looking at Texas in this particular study. It's about $30 a megawatt hour is what they're getting from subsidies. So they get whatever they sell the electricity for, and then they get this $30 per megawatt hour payment. And it depends on how much they produce. So it's not an upfront subsidy. It's when you produce a unit of electricity, you get the subsidy. Right, so 40 to 60% of their revenue is coming from subsidies. 40 to 60%. So these subsidies are very, very important for their bottom line. Right, and they're really driving wind investment, and you can see this from subsidy expirations. So here we have in 1999, we have our first spike in wind power. It turns out in the year 2000, those subsidies expired. So investment in new wind power plants dropped to almost zero. In 2001, those subsidies were reinstated retroactively. Right, so an important aspect of this is actually the production tax credit, not the renewable portfolio standards. So the production tax credit accounts for about 2/3 of that $30 subsidy that I was showing earlier. Yep. Yes. Yes. Mm-hmm. So it constitutes 40 to 60% of the revenue, right? So it's a really big part. It's no wonder that no one decided to invest here, right? And that people did decide to invest here. An important aspect of the production tax credit is that once you receive the tax credit, you get it for 10 years. So there's no uncertainty. It's not like, well, I'm going to install this year and maybe I won't get the tax credit next year. It doesn't work that way. So as long as the tax credit is active when I build my turbine, then I get the tax credit for 10 years. So you can guess again when the subsidy expired and again was renewed retroactively. You don't have investment going to zero. There was some expectation here that actually it would be renewed retroactively, but still firms were hedging their bets. And they're like, well, I don't know for sure it's going to be retroactive. I'm not sure that it's going to be reinstated. So you see these investment drop-offs. Now this isn't conclusive, but this is evidence that further evidence of the importance of these subsidies for wind power plants. Okay, so there's a number of ways we could approach looking at substitutes, these short-run substitution I was talking about. So we could use an engineering model that's completely static, right? Some of the characteristics we want to incorporate, though, are dynamics. So if I have a generator and I start it up and it's in the morning, you have very short-run dynamics. It costs me something to start it up. I may not want to shut it down again for a certain period of time. Other things we want to include is location issues. So like if I'm close to wind power, maybe that affects me more than I'm further away, just depending on the configuration of the grid and where there is congestion on the grid. So I want to take into account location. We also want to take into account market power. So this is important given the way that many markets have been restructured. If certain firms can exercise market power, we want to account for that. That is, by market power, what I mean is that they're not pricing at cost. Right? They're including some markup above their cost. So another approach is to use an engineering model that incorporates dynamics. And this will account for locational issues and also dynamics, but not market power. What I'm going to be doing is taking an econometric approach, which accounts for dynamics, location, and market power. Three of those. And so the approach is to take quasi-experimental variation and the amount of electricity produced by wind turbines. Right, so this is just driven by weather. So on a windy day, they can produce a lot of electricity. On a day that's not windy, they can't produce electricity. And I'm using very fine scale electricity data on generator output. So I have wind output every 15 minutes. And I also have the output of every generator in the market every 15 minutes. So this is going to allow me to identify generator-specific substitution patterns. So let me take a generator in West Texas that burns gas. It was built in the 1970s. It uses steam it uses gas to produce steam to drive a turbine. Right? So what I'm going to actually get is a generator-specific substitution coefficient. For every additional megawatt hour of wind power produced, on average, how much does this generator reduce its production? So it's very specific to each generator. In that sense, it's very, very flexible. There's no aggregation going on here. Right, so once I know which generators reduce their production when wind power comes online, then I'm going to use EPA generator profiles. So the EPA tracks emissions from generators, and they can tell you, what their emissions rate is. How much sulfur dioxide do they produce per megawatt hour? How much carbon dioxide do they produce per megawatt hour? How much NOx do they produce per megawatt hour? And I'm going to apply these generator profiles to the substitution coefficients I'm going to estimate to get offset emissions. And then I'm going to take the emissions and value them and compare them to the subsidies that we're using to induce investment to produce wind power. Sure. Yes. Yeah. Mm-hmm. Mm-hmm. Yes. Which people are you talking about? Okay, so let's suppose I'm a generator that burns coal, okay, and wind comes up, the price, wind power increases. So what actually happens in this market? Well, the price of electricity drops. So there's a real-time market every 15 minutes. So wind power starts increasing. It may be anticipated. It may not be anticipated. That's sort of up for debate, how much of it's anticipated versus not. So the price drops. And the price will continue to drop until some generator on the grid decides it's worth it for me to reduce my production. Now, maybe I contracted to provide electricity to someone else, but now the price is below my cost of production. So I can lower my production, buy power on the spot market to meet my contracts, and earn money in the process. Earn more money than if I had been producing electricity myself. So that's the mechanism by which this happens. There is an explicit price process, right? And you'll see actually in Texas that these prices, especially getting into, not so much I'm looking at data from 2005 to 2007, but particularly in 2008, where you have prices being very, very low in high production time periods for wind. We're talking negative, right? So the price is below zero. Now, why would the price be below zero? Very odd, right? And the reason is because they're getting this subsidy. So wind farm actually is not going to turn off unless the price is below minus $30 a megawatt hour. Because for every unit of if they have zero marginal cost, or close to zero marginal cost, for every unit of electricity they produce, they're still getting money even if the price is zero. Still getting $30 a megawatt hour. And so you see prices that go very, very low. In fact, you'll have prices, in 2008, you had prices that for 4, 5, 6 hours at night would be below zero. Because they just don't want to turn off. And they have to convince another generator to turn off. And those generators don't want to turn off either, partly because of these dynamic considerations where if I turn off completely, then I have to start back up again, and that's costly for me to do. Exactly. It's so costly for nuclear to turn off, it's just never going to do that. And the marginal cost of nuclear is very, very low compared to coal and compared to gas. So there's always other generators that are willing to turn off before you ever get to nuclear. Good question. Okay, so there's actually, at least when I started this, there's been much more work since I've done this. There's actually little empirical research on quantifying offsets. So there were quite a few engineering simulations for what might happen as you had electricity, like should we build another gigawatt of wind power on our grid? What implications are those is that going to have for things like reliability? And they used engineering models to do that. They're very good at looking at things like reliability. And in the process, they're like, well, we can tell you what the emissions change will be. This paper, on the other hand, actually uses data on operations to measure the environmental offsets. Right? So I'm actually looking at a grid with operating wind farms, and I'm using the actual observed behavior for generators in the market. And actually, this has spurred follow-up papers by Caffeine and Novan. They look at other grids in the United States. Like I said, I'm looking at the Texas electricity grid. And they also answer slightly different questions, looking at, for example, heterogeneity by time of day. The parameter estimates I'm going to be showing you are on average, right? But we might care about when do these emission offsets happen in the course of a day or in the course of a season or by level of demand, right? And so that's what these other papers do. All right, so this is the kind of variation I'm using in the data to identify substitution patterns. So this is daily. I don't have it up here every 15 minutes, just for simplicity. Right, so here we have, this is just 2 weeks I chose, sort of at random. Not completely random because I chose the first week of 2 months, right? So yeah, the first week of here in December 05, you see, you're going from 8 to 14 to 12 to 6 to 4, 10, 13. And likewise here, you just have a lot of variation in the amount of wind power produced on any given day. Right? And this is not something that the wind farms are choosing. Right? Remember, they're going to produce electricity whenever possible. Right? Even if the price is very, very low, they still want to produce electricity. All right, so I'm going to argue that wind power is exogenous. And by exogenous, I mean determined outside of the model. So I've already gone through some of these arguments. Basically, we have these high capital costs, low operating costs. Fuel is free, minimal maintenance. It means a very low marginal cost producer. They get renewable subsidies, and they only get those if they produce electricity, regardless of what the price is. And the result is whenever the wind is blowing, these guys are trying to milk every last ounce of energy they can out of wind power, with the exception of times when price is very, very, very low, and they're like, okay, it's minus $40 a megawatt hour, we're going to ramp back production. Or there may be certain events, like when you have a hurricane or something, you just have to turn it off. Right? There's nothing you can do about it. Okay, so we might think of an experimental model. Since this is exogenous, it is highly variable, where we just have the quantity production from a given generator on the left-hand side, and then wind on the right-hand side. This is a very, very simple model, right? But the problem is that this isn't an experiment. It's quasi-experimental in that wind is not completely random, right? So it follows some patterns. So if we look over the course of a day, here we have wind output. It's high, like we start at midnight here. So it's high at midnight, kind of drops off towards the morning. During peak demand times, it's at its lowest levels. And then as demand tapers off, it goes back up again. Right? So it's strongly negatively correlated with demand for electricity. This is not what you want from a production technology. This is not unique. Also, this is not unique to Texas, but pretty much all through what they call the wind belt, which is the Midwest in the U.S. We have this kind of production pattern. This is very common for actually any land-based wind farm. Offshore wind farms are different. They have a production pattern that's more similar to demand. Okay. But it doesn't stop there. We also have seasonal variations. So wind produces most of its power in the spring and in the fall, which is exactly when we don't have high demand. We have high demand in the summer and in the winter. In this case, for Texas, it's particularly in the summer because it's a lot of air conditioning. But that's true throughout the US. The peak demand times are always in the summer because even in Minnesota, they use air conditioning. So the grid I'm going to be looking at is the Texas Interconnection. It's been a restructured market since 2001. There's about 22 million people here. It has a relatively large share of wind power. So in 2007, it had 5%. 5% of its capacity was wind, which for the US is quite high. It's also importantly isolated from other grids. So less than 1% of the power produced in Texas is exchanged across its border. That means that I can see which generators are substituting for wind. Right? If all the power was going outside of the grid, I wouldn't know who was substituting for that. So this gives you a visual overview. So it's this area right down here that we're going to be looking at, the nation of Texas. So the data I have is generator output every 15 minutes. So I have 332 generators I'm looking at, plus the wind farms. I have it for 2 years. I also have DC ties. These are the transmission of electricity outside the grid. So I do see how much electricity goes outside the grid. I just don't know what it does once it leaves or where it comes from if it comes in. There's 2 DC ties. One is to the Southwest Power Pool, and one is, I forget the name of it, but it's the southern grid. So it is point to point. It's just transferring power between it and another interconnection. Okay, so I have plant level or generator level emissions data. For CO2, I have generator level. For SO2 and NOx, I have plant level. And then I'm going to convert megawatt hours of offset electricity into pounds of pollution. Right, and this just gives you an idea about the growth of wind over this period. So it goes from 2% up to over 5% of capacity in Texas. Right, Texas has a lot of natural gas. About 64% of capacity is natural gas, and only 20% of capacity is coal. So it's a relatively clean, as far as electricity grids go, relatively clean electricity grid. Okay. So interestingly, this change in capacity in ERCOT represents 25 to 30% of the total US wind capacity built over this period. So even though I'm looking at Texas, it represents roughly, so let me rephrase that. It represents roughly half of the capacity built in response to subsidies, which is 25 to 30% of total US wind capacity. So Texas is a huge player in wind in the US. So at any given time, up to 10% of power on the grid is coming from wind. Now that's even more, and it all stays within Texas. I'm going to kind of go through this quickly. So demand in, many of you probably are not worried about this, but economists worry about demand and supply, what's endogenous, what's exogenous, what's determining what. And in electricity, you have that demand is actually not determined by wholesale prices, the demand for electricity. And that's because consumers are like you and I, and even to a large extent, industrial users are not exposed to wholesale prices in real time, right? So I get some price, maybe it's a price for the month, maybe my price changes every month, that's fine. But for that given month, I have no incentive to increase my consumption when prices are low or decrease it when prices are high. I just face some constant price. So I'm modeling demand as a function of shocks, Z. So this might be the weather, it might be when I wake up, it might be when I go to bed, and of some constant price that doesn't depend on T. or my T, or my 15-minute time period. So the wind is going to affect output through the price, as we mentioned before. I'm not going to model the price component of this. Rather, I'm going to use a reduced form model to look at the impact of wind on emissions or on output directly. So I could go wind on prices, prices on output. But instead, I'm just going to go directly. It's more efficient to go directly from wind just directly to output. And I'm going to exploit the exogeneity of wind power to do that. The fact that they don't have control over their available fuel, they're a low-cost producer, and they cannot store their fuel or their output. So you could look at a static econometric model. This is one that would say, let me look at output of generator A right now in this 15-minute period, and let me look at how much wind is being produced this period. And I can just do a regression and look at the correlation between those two. Right. I would want to control for the fact that wind power may be correlated with other incentives, such as demand, temperature, congestion. Right. So if I'm in a congested time period, that's going to alter the way that wind power affects a particular generator. And things like temperature can actually affect the efficiency of the generator, as well as just the overall demand on the grid. Right. So if there's just, if I were just to regress output of a generator on wind, I would get a very, very negative coefficient, because wind produces most of its power when demand is low. And so I'd say, wow, this generator is reducing its production at night, and wind power is going up. Man, wind power is really offsetting this generator. But really, it's that generator is ramping down for other reasons. So that's why I need to include these controls in there. I also include date dummies. So for every date in the data, so I have 365 times 2 date dummies. So anything that's peculiar to the day is encapsulated in these date dummies. So for example, gas prices change daily. Retail prices are changing, right? Although they're constant within a day, is what I'm assuming. You may have a given firm that's having an outage, right? So the fact that it's producing 0 today may not have anything to do with wind power. It may have to do with the fact that it's broken. So these date dummies will, any variation that happens across days will be encapsulated in these date dummies and thrown out of the, it won't contaminate the estimates of offsets. Okay, so this is what the estimating equation would look like. I have quantity on the left-hand side. I have wind and wind squared. It's just a simple polynomial expansion of wind to allow for nonlinearities, which I think may be in the model. You have z, which are all those controls like demand and temperature, and then you have the date dummies. Right? And there's going to be a separate regression for each generator on the grid. So I had 332 generators. That's 332 regressions I'm going to be running. And I'm going to get generator-specific substitution coefficients, which are the beta 1 and the beta 2, right, in my model. And I also do a quadratic expansion for the controls to allow for nonlinearities there. This is a nonlinear system. Okay, this is the estimation. Right, not that interesting. Okay, so these are the results from a static model. Not, what's the ratio? Whether I should have a beta, whether I should have wind cubed in there. So I don't know if it converges. Like if I were to add more and more, I know that when I add the squared term in there, it is statistically significant, right? So it is explaining something in the data. So in that sense, it belongs. I did do the same thing with the cubed. It's been a long time since I've looked at it. My recollection is that it didn't matter, but I would need to double check that. So the basic idea is I do want to allow for some nonlinearity. I also want a fairly parsimonious specification so that the interpretation of the coefficients is straightforward. But that is some. I don't see any theoretical reason why you could rule out, for example, having more polynomials in there. Could, yeah. Okay, so if we just look at the static model, and by static, I mean that it's just the output right now and the wind power right now that matters in this time period. You see that coal actually accounts for a large fraction of the substitution. So for every megawatt hour of coal, about 18% of that, 0.18 of that 1 megawatt, comes from coal. Coal plants reduce their production. This is a little counterintuitive because although wind power does produce more electricity at night, coal is more likely to be on the margin then. Maybe that's important. Gas accounts for 85% of the substitution. Nuclear, there's just a couple of hydro facilities, they're very small. Nuclear accounts for a very, very small portion, as does imports and hydro. So the problem with a static model is that the evolution of the market determines current behavior. So it's not just how much wind is being produced now, it's how much wind I expect to be produced in the future. Right? And it's not just what I'm operating at now, it's how long I expect to continue operating in the future. So these firms are forward-looking. They know that's going to be costly to turn on and off their generators, and so they're going to take those things into account. So the current state of the market is not going to be sufficient. The past and the future are also going to matter. Right, so the way that firms optimize in this market is they have information 2 hours prior to operation to decide what to bid. So this is all happening through bids. Firms submit bids into the market. There's an auction, and they say, okay, you win the bids, you produce this electricity. Right, and that happens 2 hours prior to the time when they have to produce the electricity. Right, so this is happening every 15 minutes. So they're going to choose some optimal policy. You're going to solve a complicated dynamic programming problem. They're going to choose some optimal policy 2 hours before production. So I'm going to include this information, controls for the firm's information set, into the model. So I have the contemporaneous variables, and then I'm going to have these lagged variables. So lagged 9 to 100 periods. I'm going to have wind power lagged, right? So how wind matters. I'm going to have demand lagged. I'm going to have temperature lagged. I'm going to have congestion lagged. I'm also going to have the operating state of other generators lagged 2 hours. So if I care about who's operating when it's my turn to submit a bid, I might care that you're operating or you're not operating. So I include that information in there also. Yep. Mm-hmm. It does not. It does not. There's no storage capacity on this grid. They have been looking at doing, there's a lot of salt mines or salt formations in Texas, so they've looked at doing compressed air storage, but there's nothing there. There's definitely not any pumped hydro storage. If there were piped hydro storage, that complicates the analysis considerably, right? Because now I have to think about, well, maybe if you had a lot of pumped hydro storage, what you would find is that hydro substitutes for all of wind power, right? It just sort of soaks up the wind power and lets it out later. And so you'd have to have a different kind of approach. I don't think there's, it depends what level of penetration you're looking at. So far, there's no reason why you would need to have that kind of storage. One kind of storage you can have is not to produce electricity using gas, right? That's storage. Right? So if I just don't produce electricity using gas during certain times of the day and I produce it other times of the day, that's basically costless storage there. Now, as wind power penetrations increase more and more, it may be very costly for generators to turn on and off. So it may be economical to incorporate some storage. In the extreme case, where you actually have more wind power being produced than anybody is demanding, that's the case in which you'd have to have some kind of storage or a way to dispose of the electricity. But for even relatively high levels of wind power, it's not clear that you need any storage. It might be economical to have storage, might make sense, but there's no sense in which you need it. Okay, so this is the dynamic model. So again, I have the same sort of estimation, right? And then here are the dynamic results and the static results. So what you see is that first, of all, right off the bat with coal, if you look at a static model, you think that coal really is impacted by wind. If you look at a dynamic setting, actually that's not the case anymore. So coal accounts for a very small fraction, and statistically it's not even significant of offsets from wind power. And gas now accounts for 92% of all offsets. So this actually corresponds with maybe what our priors were about who should be reducing production when wind power comes online. Right, we think it would probably be mostly coal. Interestingly, though, a lot of it comes from combined cycle generators, which are the most efficient generators on the grid. So over half of the offsets come from these combined cycle generators. Turbines, those are the sort of the easiest ones to start up and shut down, account for 7%. And steam, which tend to be the highest cost, one of the higher costs, turbines. Well, they're a little bit lower cost than turbines, but they're still relatively high cost, account for 32% of the changes in production. All right, and then you have, again, you have here very small fractions of hydro and nuclear, and then some of which are, nuclear is still statistically significant on the margin, but only barely. Imports now go from being positive to negative, so saying that we export about 7% of the electricity that's coming from wind to outside the grid. So accounting for the fact that there are these dynamics is important when it comes to estimation. All right, so now I'm going to take these estimated parameters, which give me electrical output reduction, apply them to the EPA emission rates, and sum over all the units to get total emissions offset. Right, so here we can look at offset carbon dioxide, sulfur dioxide, and NOx. So let's focus, I have both the static and the dynamic results up here, but let's just focus on the dynamic results. And here we can look at the total market. This is broken out by type. So you can see that for every megawatt hour of electricity that is produced, about 947 pounds of carbon dioxide are offset. So less than a ton of carbon dioxide. Very small amounts of sulfur dioxide are offset. You notice that in the static model, we have significant amounts of sulfur dioxide being offset due to the fact that 18% of the production was offset from coal in the static model. And then we have less than a pound of NOx being offset from this production. Okay. So if we were to look over the whole, if we were to apply these parameters to the whole time period, and there's probably some heterogeneity over this time period, then this is what we would get: about 5 million tons of 5 million, sorry, pounds of carbon dioxide, very little sulfur dioxide, and a little bit of NOx. And as a percent of total emissions, you see that it's under 2%, whereas wind production is just about at 2%. So wind offsets emissions that are less than sort of the average emissions profile in ERCOT, right? Because it's offsetting these relatively clean generators in Texas. Okay, so I do some robustness checks, which I'm going to kind of skip through. Basically, here there is some data, continuous data on emissions from generators. That is, in real time, every hour, they measure the emissions output. And so but it's not for the whole set of generators. It's just for a subset of them. So I look at the subset of those generators, and I find that for CO2 and SO2, the offsets are not statistically different. For NOx, the offsets are much lower. So we actually get even lower offsets for NOx when we look at real-time emissions as opposed to the average emission rates, at least for these subset of generators. Okay, so how are we going to value these emissions? So let's suppose that these are the emissions that are being offset. Okay. So for unregulated emissions like carbon dioxide, these are real reductions in carbon dioxide. Right? This is carbon dioxide that would have gone into the atmosphere that now is not. And we can use estimates of marginal damage costs for carbon dioxide to value that. For regulated emissions, such as NOx and SO2, these particular emissions are regulated under cap and trade systems. So if I save some emissions now by not producing, I can keep a hold of my emission certificates for later. So there's no change in the aggregate level of emissions. for these emissions. That is, there's no social benefit from reduced emissions unless the new distribution of emissions over time is different. So if now we're emitting at night instead of during the day, well, maybe that's beneficial to people. Or if we're emitting during the day rather than at night, maybe that's worse for people. But I'm not looking at that. So I don't have the information to look at that kind of heterogeneity. For NOx, though, it turns out that the NOx caps are not binding in Texas. So even though there is a cap and trade system, it basically doesn't matter because the permits are basically free, right? Because I'm not hitting the cap. So there's no penalty for me emitting more in Texas. This is particular to Texas. This is not true, for example, on the East Coast. Okay, so let's look at high, middle, and low values for these emissions, right? So, I'm only looking at NOx and CO2, right? So these are the sort of the range of values. For CO2, I'm taking, these values come from a report that was produced a couple of years ago by the US government trying to synchronize the valuation of carbon dioxide benefits across its agencies. And they came up with a range of values between $5 and $35. So you can see here, if we translate these numbers using our estimates, we get the value of the offsets in terms of dollars per megawatt hour of wind power. So, yes, they do. Depends on what day you ask. It goes anywhere from $40 to 0. So, like in the first stage of the ETU, it was in the beginning. It was in the $40 range to begin with, and then about halfway through, it crashed and went to 0 when they realized that they gave out too many permits. Yeah. And now the second stage is now in place. I'm not sure what they're trading at now. I'm guessing it's around the $30 range, but I don't know for sure on that. I haven't checked that in a while. So here we're looking at a value of carbon dioxide emissions of around $16. And for NOx, we have, because so little NOx is offset, even though it has a relatively high price, it doesn't contribute much to the value of total emissions offset. All right, so the value of offsets is going to be driven by carbon dioxide emissions. That's where all the benefit is coming from. Right, if we take a discounted stream of subsidies at $20 per megawatt hour over a 20-year wind farm life, because remember, the subsidies are only for 10 years, but the wind farm isn't going to shut down after that. Once they're in the ground, they're going to keep producing. Right, so if we take a 20-year wind farm life and we have renewable portfolio standard credits that are worth $10 for the life of over the life of the wind farm, right? Then this is justified if the social cost of carbon is greater than $42 per ton. So if we thought that a ton of carbon dioxide was causing $42 in damage to the planet, then we would want to have these subsidies at the levels that we have them. That's what this is saying, right? The government's central value is $21 a ton, right? So it's definitely not the least cost option for reducing carbon dioxide emissions. This is sort of a separate point. So here, we're having a hard time justifying the subsidies unless we think that carbon dioxide is relatively expensive to emit. And even if that was true, this is probably not the least cost option of doing this. There's many other options that we have to reduce carbon dioxide emissions. It's not clear what the least cost option is. So an economist would say, well, we should put a tax on carbon dioxide of $42 per ton and see what people do. Right? If that's what we think that if this is the damage for CO2, because people respond in ways that we don't anticipate. Right? We have technology. We think we have technological solutions. We can apply them. And if we know that that is the only option that's out there, then that's what we should do. We actually don't need a cap and trade system or anything like that. If we know what to do, we should just do it. The point is, though, that we don't always know what to do. We don't know what innovations are coming. We don't know how people are going to respond to incentives. And so actually putting some sort of an explicit price on carbon dioxide aligns those incentives across the whole economy. So I'm out of time. There is some, the question is, can we generalize this? So even if we can't generalize it, half of the wind capacity installed due to subsidies comes from Texas. So it still gives us an idea of what we're getting for half of our subsidies. And you can look at regional results and compare basically what is the generation mix in Texas compared to other places in the US. Texas turns out to be one of the cleaner grids in the US, right? So in some sense, we might think this is more of a lower bound on the emissions offset that we might get in other areas of the US. But it's a little hard to generalize. Okay. Go directly to conclusion. Right, so this research evaluates a large part of a $1 billion a year subsidy and looking at half of the capacity installed due to those subsidies. And it may be a lower bound or returns elsewhere. And you can do this because you have this really interesting variation in wind. Right? You have weather. Weather is a great instrument for estimation. And the results show that the value of the offsets are being almost completely driven by carbon dioxide emissions. Right? And if you believe that $42 is an appropriate price for carbon dioxide, there's many people who do believe that, then you could say, well, for plausible values of, it's not $500 a ton, right? It's $42 a ton. So for plausible values for CO2, the subsidies might be able to be justified. Okay. Any questions? I'll take applause. That works. That works. Questions? Mm-hmm. Mm-hmm. So the problem is no matter what grid you go to, you're going to have a hard time offsetting coal plants. Given the way that prices were in 2007, 2008. The way the prices are now may not be such an issue. Right? The difference between gas and coal prices, input prices, has really shrunk. Right? In fact, earlier, a year ago, it was cheaper to produce using gas than coal. Right? And so in that case, you would have offset potentially all coal production. As far as how you extend this to other areas, like I mentioned, there have been other studies which have done this. They found that, for example, in California, that the offsets were even lower than in Texas. In the Midwest, they were somewhat higher, but still you get most of the substitution going with gas, just because it's hard to get those coal generators offline. Mm-hmm. Yes. So you're still going to have the same patterns of production that you would if you had electricity being produced by wind in the Midwest as opposed to being brought in from North Dakota. So that part of the equation is not going to change. The question is, if you have at what level of penetration do you really start offsetting some of these dirtier power plants? I don't see any reason why coming from North Dakota would be different than just being in Kansas or Missouri. Sure, maybe that's where the available. Although some of the largest wind producers are actually in places like Iowa. Yeah. So I think that's really a matter of sort of as we increase the penetration of wind power, as more and more of the electricity comes from wind, how are these estimates going to change? And they definitely are going to change, right, as you get higher penetration. So one thing to do, actually in Texas, they've continued to build wind power, right? And so one could do a follow-up study on this and look in 2012 and see what you're getting from the same sort of thing. It kind of misses the point though, because when you're looking at a significant amount of wind power being produced, or in a particular area, that really changes which generators want to even be there, right? So you may have that this increases the amount of gas generators that can respond to more volatile prices, right? And maybe that's bad for coal generators. Maybe it's not bad for coal generators. And that's the long run question that really needs to be answered is what are we going to get when we go to 30%, 40%, 50% wind? How is that going to impact the types of generators that can operate profitably on the electricity grid? No, it's not. It's not life cycle. So it's just at the smokestack. So any additional emissions that come from like the drilling of gas, the mining of coal, and if you can reduce if you're reducing the consumption of those fuels, so you have less mining, you have less drilling, you're also going to save those emissions. Mm-hmm. I don't think I would have a technology-specific policy, like saying I'm going to choose these winners and I'm going to subsidize these technologies. So the arguments that are often used are that if we don't do that, this is sort of an infant industry. We're going to have innovation. Things are going to get cheaper. I have other research that is actually looking at this, and my argument is that if we're going to subsidize something, we should subsidize R&D. We shouldn't be subsidizing production. If we really want to have technological improvement, because this is sort of a backdoor way of doing that. The idea being that if we subsidize the production, then there'll be more demand and there'll be more R&D. So it's sort of like 2 or 3 steps removed. But if what we really care about is R&D, we should just subsidize R&D and provide more research dollars to people like you to do the research. Mm-hmm. Hmm. Yeah, right. I don't know the answer to that. I do know that even the point-to-point lines have received a lot of resistance, either because they're very expensive, but even besides that, if you take a look at the East Coast, they don't want wind power from the Midwest. There have been proposals to build high-capacity lines transmitting wind power from the Midwest to the East. They don't want it. Why don't they want it? Because they have, right now, the renewable tax credits in those areas are very high, the prices are. And they're worried that the renewable tax credits will crash and they won't have native production of renewable energy. Not only that, they're worried that once those lines are in place, not only will they take wind power, but they'll also take coal. Cheap coal electricity. When the wind isn't blowing, it's going to transmit cheap coal electricity, and they don't want that either. So there are significant obstacles even outside of the cost of these things. Even if they were justified on cost, there's sort of political ramifications that you have to deal with. Perhaps. But to sort of go back to that, I think that I think there is potential for even for point-to-point. I don't know that we need any technological advances. It's just that even the cost of that is prohibitive right now. And well, sure. If we could make it less costly, right? If we make it less costly, I think it's a great idea. I think people should be doing this kind of research, figuring out how to. I mean, not only wind is only one application. I mean, there are significant swings in demand across different areas of the U.S. And if you could just take, electricity from one area and move it to another and smooth out sort of these demand shocks, that's one reason why they created power pools, right? So there are other benefits other than just moving renewable energy from having better transmission infrastructure. Okay, great. Thanks.